Okay, so our topic for today is going to be proofs. And this is going to be a really big topic. When we're talking about proofs, we're talking about the way of logically structuring an argument to prove that some sort of statement is true. So our essential question here for today is going to be, how do I use a two-column proof to prove a statement true? Our first box here, proofs. A proof is a series of logical statements used to show the truth of a statement, right? Like imagine a lawyer, right? A lawyer goes into court. He's trying to prove that his client is innocent, right? That we're trying to structure an argument using logical statements to prove something to be true. And the way that we're going to do it is called a two-column proof. A two-column proof is a way of structuring conditional statements, those if-then statements, into two columns, statements and reasons that show an argument in a logical order. And when we're doing this, we always have some sort of information that we're starting with, and that's called the given. The given is the given information that you know is true. This is the facts that you begin with at the beginning of your case that's going to help you begin your proof. So a two-column proof, we can see the kind of format here, right here, where we've got these two columns. We've got a column of statements and a column of reasons. And like we mentioned before, the given will always be written out, and that's what we're starting with. This is the starting info. Starting information. And then they're also always going to give you some sort of statement that you are trying to prove. And this is our goal. We are trying to prove that whatever they're telling us to prove is true. So your starting information, your given, will always be written first. So that's always going to go right here. It should always be your very first thing that you write down. Sometimes you might have more than one given statement, in which case it takes up the first two rows. And for every statement that we write down, we also have to provide a reason. So our reason why we know that the given information is true will always be given. So your first reason should always be given. And then the next couple rows, could be only one more row, could be two, could be three, who knows, are going to be filled with other statements that we know are true based off of the given. And we need to provide other reasons why we know those things are true. And that little dotted box over there says that our reasons can be things like theorems, postulates, properties, definitions. It can be a lot of stuff. And we will eventually be done with our proof whenever we have our prove statement written down. So remember, the proof statement is the goal, and whenever we get there, we know that we are done. So oftentimes with people beginning to learn how to do proofs, those reasons are the toughest things to come up with. So the kind of stuff that we're going to start with here today are algebraic proofs, just based off of algebra. So no geometry really right now. We're just going to try to get used to the two-column proof structure. Now, we know a lot of things about algebra. And down below here, we've got a bunch of different properties that we know that we can use. So I'm just going to run through these real fast just so you can kind of see them written out. The distributed property, right? We know that the distributed property works, right? If 2 parentheses x plus 1 equals 10, then we know we can distribute out to get 2x plus 10 equals 10. And notice that's written as a conditional statement, right? An if-then statement. If 2 times x plus 1 equals 10, then 2x plus 2 equals 10. We know the addition property. If 3x minus 2 equals 13, then we can imagine that we are adding 2 to both sides to get to 3x equals 15. Subtraction property the same way. If 5x plus 5 equals 15, then we could subtract 5 from both sides to get down to 5x equals 10. So we can use the subtraction property. Division property, we could divide both sides by 10 to get down to x equals 6. Multiplication property, if 1/2 x equals 3, then x equals 6, right? That would be by multiplying both sides by 2 to get rid of that 1/2. Substitution property, this one's kind of tricky a little bit. If x equals 3 and x plus 4y equals 11, then 3 plus 4y equals 11. What we did there was we took 3 and we substituted it in for x, right? Since x is equal to 3 according to that first statement, we can substitute it in. Symmetric property. This one doesn't come up too often, but symmetric property lets us flip an equation around. So if 7 equals x, we can imagine that we're just flipping those to get x is equal to 7. Transitive property. If a equals b and b equals c, then a equals c. Since both a and c are both equal to b, that means that a must be equal to c. This is going to come up a lot later on in this unit. And then lastly, we got combining like terms. If 3x plus 2x equals 10, then we can combine that 3x and the 2x to be equal to 5x. So this is just a reminder of a bunch of the different properties that we have done in the past in algebra. And all of those are valid reasons that we can use when we are doing an algebraic proof. So this probably seems like a lot right now. Let's jump into the first example, and you are going to see just how easy this can be when we're doing algebraic proofs. So let's look at example 1 here. Oops, sorry. Example 1 says 5x minus 1 is equal to 2 parentheses x plus 4. Okay, so first of all, given. We know that the given statement is our starting information. And that's got to go up top. So in this case, I already wrote down the 5x minus 1 is equal to 2 parentheses x plus 4. But in future cases, you're going to have to write that down. That's got to be the first thing you write down. And then remember in the other column, we put down the reason why we know that is true. In this case, we know it's true because it was given to us. That is the starting information. And now from here, it's going to be up for us to come up with more statements and more reasons to eventually get to the point where we know for sure that x is equal to 3. But this is just an algebra equation, so we're just going to do our normal stuff, and we're just going to practice writing it down step by step by step, providing the reasons as we go. So first thing I would do is I'd probably distribute, right? If we distribute here, the 5x minus 1 stays the same. 2 times x is 2x. 2 times 4 is 8. And that was the distributive property that lets us multiply into those parentheses. Okay, so now let's just imagine we're going to keep going. We're going to keep solving this thing. Well, what have we here? Let's probably subtract the 2x from both sides, right? If we subtract the 2x from both sides, 5x minus 2x would leave us with 3x's over here. And we've only got an 8 over there. So since we subtracted the 2x, this would be the subtraction property. Okay, we're still moving here. What do we want to do next? Probably get rid of that minus 1, right? To get rid of a minus 1, we would need to add 1. So if I add 1 to both sides, 8 plus 1 is 9. So that is the addition property. And then lastly, last step, we got to get rid of that coefficient, right? Get rid of that 3 in front of the x. To get rid of that, we got to divide both sides by 3. So our last step here, x equals 3, according to the division property. Now, of course, we can easily see that we are done here because it is the last little box there, but in case you don't have boxes and you got to write it yourself, you know you're done because you got to the proof statement. The proof statement told you to show that x is equal to 3, and that's what we did. Now, this might seem unrelated to a previous lesson over conditional statements, but you certainly don't have to do this, but I just want to illustrate that this is the exact same thing as conditional statements, okay? Imagine the word if right here. If 5x minus 1 is equal to 2 parentheses x plus 4, then 5x minus 1 equals 2x plus 8 according to the distributive property. And if 5x minus 1 is equal to 2x plus 8, then 3x minus 1 is equal to 8 according to the subtraction property. And if 3x minus 1 is equal to 8, then 3x equals 9 according to the addition property. And if 3x is equal to 9, then x is equal to 3 according to the distributive or the division property. So this is literally us just laying out a bunch of conditional statements in a row to string together these conditional statements to show exactly how it flows logically. This is how you structure a proof so that nobody can argue with you. This is what Euclid did back in the day when he was going back and proving each and every one of these geometric properties and theorems that we're going to be learning in this class. You have to string it together logically, providing those reasons so that you know for sure, beyond a shadow of a doubt, that what we have shown is proven true. Okay, so algebraic proofs, not too bad. You're just doing your normal solving skills, but providing those reasons as you go. We're going to slowly inch our way into geometric proofs here next. Now, if we're doing geometric proofs, and we're not going to be doing full geometric proofs here today, but when you're doing them, we need to start incorporating some of these theorems, postulates, properties that we've learned already in geometry. So these are a bunch of different things that we can use as reasons when we're doing a geometric proof. Okay, so our first one is the linear pair postulate. The linear pair postulate says that if you see a linear pair, so remember a linear pair is two adjacent supplementary angles, like these, then you could say that the measure of angle 1 plus the measure of angle 2 must be equal to 180. So if you see a linear pair, you can use the linear pair postulate as a reason as to why those two angles must add up to be 180. Next up, we got the angle addition postulate. Now, the angle addition postulate says that if you've got two adjacent angles, so like angle 1 and angle 2 there, and maybe this big angle is angle ABC, then we could say that the measure of angle 1 plus the measure of angle 2 has to be equal to the measure of angle ABC. Those two smaller angles added together have to be equal to the big one. The segment addition postulate is next. You guys probably remember this one. If we've got three collinear points with B in the middle there, then the segment addition postulate says that AB plus BC must be equal to AC. Next up, we got the vertical angles theorem. Vertical angles theorem, I drew that too big. Let me try that one more time. The vertical angles theorem says that if you got two vertical angles, so vertical angles formed by those intersecting lines there, then they must be congruent. Angle 1 must be congruent to angle 2. Definition of midpoint. We know what a midpoint looks like. So if I've got this segment with B right in the middle, and I know that B is a midpoint, then what I can say is that segment AB must be congruent to segment BC. An angle bisector. We know what an angle bisector does. A bisector always splits things in half, right? So if you've got an angle bisector with it actually splitting those two angles into equal parts, then you know that angle 1 must be congruent to angle 2. Next, we have complementary angles. Now, I'm going to draw them to be adjacent, but they don't need to be adjacent. If you know that two angles are complementary, like if it's in the given, then what that means is that those two angles, angle 1 and angle 2, must add up to be 90. So the measure of angle 1 plus the measure of angle 2 is equal to 90. Then we got our supplementary angles. Now, I'm going to draw them separately here, not being adjacent, just because we already had the linear pair postulate that showed them being adjacent. So if we know that they're supplementary, then we know that they add up to be 180. The measure of angle 1 plus the measure of angle 2 is equal to 180. And then lastly, we have the definition of congruence. And you guys might have noticed this as I was writing down these statements here. Sometimes I was using equal signs and sometimes I was using congruency symbols. And that's an important distinction. We use equal signs when we're talking about numbers. So if I'm like adding things up to be equal to 90 or adding things up to being equal to 180, or just adding things in general, you have to be using equal signs because you can only add with numbers, right? You can't add with things like angles and segments and stuff. So if you ever need to switch back and forth between equal signs and congruency symbols, that's when we use the definition of congruence. So what we could do here is if we want to go from, for instance, angle A is congruent to angle B, and we want to switch that to the measure of angle A is equal to the measure of angle B. If we want to switch back and forth here, either going from the congruency symbol to the equal sign or the equal sign back to the congruency symbol, that's when we use the definition of congruence. Because congruent angles, by definition, means that their measures are the same. Or if you want to write this one over here too, you can. The same thing works for segments. So if you're trying to go from, for instance, segment AB is congruent to segment BC, and you want to switch to the length of AB is equal to the length of BC. If you want to switch going this way, you can also use the definition of congruence for that one. So it works for segments and angles, but if you're ever needing to switch between equal signs and congruency symbols, that's when you use the definition of congruence. Okay, so that was a lot. Let's go take a look at the examples that we're going to be doing today. At most, we're going to be using one of these things here today. These are just all the different things that we know so far. So let's hop up to example 2, and we'll see what I'm talking about. So this says, given B is a midpoint, we want to prove that X is equal to 3. Okay, so don't let yourself be overwhelmed so far. We know we need to start with the given. All right, given goes up top. So let's go jot that down. We know that B is a midpoint. Okay, cool. Now we ask ourselves, what does that mean? Well, what does it mean if B is a midpoint? Well, according to the definition of a midpoint, that means that those two segments are congruent, right? AB is congruent to BC. And that'll be helpful. So let's jot that down. If that thing's a midpoint, then AB must be congruent to BC. And how do I know that? Because the definition of a midpoint. Okay, so now we're trying to prove that X is equal to 3. And if AB is congruent to BC, then that should mean that those two lengths are also the same, right? If it got divided into two congruent parts, that means that the length of AB must be equal to the length of BC. And this is probably the trickiest moment right here. What I'm going to do is I'm going to switch from AB's congruent to BC to the length of AB is equal to the length of BC. And that's by the definition of congruence. Remember, if we need to switch from congruency symbols to equal signs, we use the definition of congruence. And the reason that I did that is because I know what the length of AB is. It's on the diagram, right? The length of AB is 3x plus 1. And I know what the length of BC is. It's also on the diagram. It's 10. So what I'm doing here is I'm substituting in the values of AB and the value of BC. So this is substitution property. Okay, so we went through the tricky part. Now we actually just have an algebraic equation, right? We set it up geometrically, we switched it over to the equal signs, and then we substituted it in the algebra. Now I can just subtract the 1, right? Subtract the 1 from both sides. 3x is equal to 9. That's subtraction property. And then I can divide by 3. And x is equal to 3. And voila, we have proved why x is equal to 3 by showing every single step along the way. Now, just to reiterate one more time, this is a series of conditional statements. If B is a midpoint, then AB is congruent to BC. And if AB is congruent to BC, oops, I wanted the other color. If AB is congruent to BC, then the length of AB is equal to the length of BC by definition of congruence. And if those lengths are the same, golly, it didn't switch colors again. And if those lengths are the same, then 3x plus 1 must be equal to 10 by substitution. And if 3x plus 1 is equal to 10, then 3x is equal to 9 by subtraction property. And if 3x is equal to 9, then x is equal to 3 by the division property. So we can kind of imagine those conditional statements being strung along. Cool. Okay, so by far the trickiest part there, remember you got to set it up geometrically by providing the geometric reason why those things are congruent. And then in this case, since our definition of midpoint had it being congruent, we had to switch by definition of congruence into the equal signs so we can start doing some algebra things. All right, let's go down to example 3, our last one before y'all are going to try some. Let's see here. So it looks like we actually have two givens here. It says that ABC is 3x plus 9, 9x plus 10, and then 9x minus 10 is CBD. Okay, so let me jot those down first. We know we got to start with our givens. So I've got that the measure of angle ABC is equal to 9x plus 10, and the measure of angle CBD is equal to 9x minus 10. Both of those are given. So we start with our given. We get those written down first, always, every single time. Now, sometimes, guys, they're not going to have the diagram marked. It's a good habit to get into to mark your diagrams yourself. So I'm going to throw those angles in there just so that I know which one's which. And then looking at my diagram, if I'm going to try to set up some sort of equation that's going to let me solve for x, I need to write it out geometrically first. And this illustration here, this diagram, is definitely a linear pair. And what do we know about linear pairs? The linear pair postulate says that those two angles, angle ABC and CBD, must add up to be 180. That's what the linear pair postulate says. And now we know what ABC is and we know what CBD is. And since this is already written out with equal signs, we don't need to do any sort of definition of congruence things here. We can just go ahead and substitute in. ABC is 9x plus 10. CBD is 9x minus 10. And that was me substituting in the numbers for the letters. That's the substitution property. And then what can I do? Well, 9x and 9x make 18x. 10 minus 10 is 0, so that's gone. And that was me combining like terms. And then let me just divide. Get x is equal to 10 using the division property. And I know I'm done because I got to the proof statement. And there we go. So once again, we wrote it out geometrically first, and we provided one of these geometric reasons over here as to why we were setting up our equation. We already had an equal sign, so we didn't have to do the definition of congruence to switch. And then we just did our algebra from there after we substituted in. So hopefully we're feeling a little bit better here. I know that these things can be tricky to begin with. But now is your turn. You got one algebraic proof to try out on your half sheet, and you've got one geometric one to try out. So pause the video here, give them a shot, and then come back and see how you did. All right, so this first one hopefully went well. Definitely should have started off with our given here. Then we should have combined some like terms to 10x minus 5 is equal to 8x plus 5. After that, probably would have been good to subtract. Subtract that 8x. Little subtraction property. Then I'm going to add the 5 over. So that's addition. And then lastly, we just divide. So we should have ended with the division property. Okay, got to x equals 5. The second one here, we've got two givens. We've got AED is 9x plus 1. And CEB is 7x plus 23. And those are these angles. Okay, now those two angles are definitely vertical angles. And I know that vertical angles are congruent. So I'm going to say angle AED is congruent to angle CEB by the vertical angle theorem. Now, I want to set those things equal to each other so that I can solve for x. And if I'm going to set them equal to each other, then what I really need to do first is switch them to the measures, because the measures are equal. The angles are congruent. And anytime I switch like that, remember that is the definition of congruence. And now that I've got the equal sign, now I can actually replace those measures with the values that we have written down. So that's substitution now. Okay, now I can subtract. I'm subtracting the 7x. And then I can subtract the 1. So another subtraction property. And then I can divide. Get x equals 11. And there we have it. That one was kind of tricky with the definition of congruence having to be thrown in there. Hopefully you guys caught it. And if you didn't catch it, hopefully you'll catch it next time. And that wraps this up.